Hello, welcome to the lecture called Mixtures of Gases and Gases in Chemical Reactions. This is the last part of chapter 11, which is all about gases and how they behave and gas laws and all the stuff we've been talking about before. And so let's wrap this chapter up with this last lecture. All right, so let's talk about mixtures of gases. So lots of gases are basically not pure. They consist of mixtures of gases. So if you think about the air around you, in the atmospheric air, what you're breathing in is not pure oxygen. It's actually 78% nitrogen, 21% oxygen, and then kind of 1% of everything else. So according to the kinetic molecular theory, each component in a gas mixture acts independently of the others. Because remember, gas molecules don't have any attraction to each other, and they are moving very fast and very spread out with no interactions. So each component basically acts independently of others. They're not attracted to each other or react with each other. So that being said, the pressure within a gas mixture is the sum of all of the partial pressures of each of the gases that are in the mixture. Okay, so partial pressure is the pressure due to any individual component in a mixture. So if we have the total mixture, we can, and we know the percent of it, right? Then we can figure out the partial pressure of a certain gas. So for example, we've got, what is the partial pressure of nitrogen in the air at 1 atmosphere? Well, if 1 atmosphere, that's our total pressure, all right, of the gas mixture. And we know that according to research that nitrogen is 78%, calls for 78% of the air in the atmosphere. So if we take 78% times 1 atmosphere, right, we'll get the partial pressure of 0.78 atmospheres. So of the 1 atmosphere that all of the gas puts on us as we're sitting here in class, 0.78 atmospheres of that is the nitrogen. Okay, so if we have the percentage, you can always just multiply the percentage times the whole to figure out the part, just like using percentages in regular math. All right, so Dalton, long time ago, one of the first to really study chemistry and pressures, I should say, and also atoms and all that stuff, came up with a law of partial pressures. He says the sum of the partial pressures of each of the components in a gas mixture must be equal to the total pressure. So if we have a bunch of different different gases in a mixture, then all of those partial pressures add up to the total pressure, right? So here's another example down here that goes along with that. It says in the atmosphere, the partial pressure of nitrogen is 0.78 atmospheres, oxygen is 0.21 atmospheres, and argon is 0.01 atmospheres. What is the total pressure? Well, super easy. You just add them all together. So 0.78 plus 0.21 plus 0.01, we get 1.0 atmospheres. Okay, add them all together, you got the total pressure. Pretty simple. All right, so let's go over one more example. Here's an example that says a mixture of helium, neon, and argon has a total pressure of 558 millimeters of mercury. If the partial pressure of helium is 341 millimeters of mercury, and the partial pressure of neon is 112 millimeters of mercury, what is the partial pressure of argon? Okay, so if we know the total, 558, and we have all of the parts, we can figure out what the missing part is, right? So we've got 341, 112, and then we've got our X for argon. So it's just simple algebra. Put them equivalent to each other on both sides, solve for X, and you get 105 millimeters of mercury. That's the difference. So pretty simple when it comes to partial pressures of gas mixtures. All right, let's talk about the partial pressure of oxygen a little bit. So our lungs were made to breathe oxygen at a partial pressure of about 0.21 atmospheres, give or take, right? We go up, in the local mountains, and our bodies can adjust pretty well. If we go, down to Death Valley, which is below sea level, again, our bodies adjust pretty well. But typically, our lungs are made to breathe oxygen at the partial pressure of 0.21 atmospheres. So if we climb a mountain, the partial pressure does decrease, and our body can adjust for that. But if we go too high in elevation, say Mount Everest, which is like 34,000 feet, which is crazy. If you think about it, I think Big Bear is like 4 or 5, so it's, way bigger than our local mountains. Anyways, the partial pressure of oxygen up at Mount Everest is only 0.065. All right, so there's not much oxygen up there at all. So you can see, and if you've ever, seen pictures or videos of people that climb Mount Everest, they need to wear oxygen masks so that their lungs can be breathing the correct amount of oxygen to feed your body. So if you have too low level oxygen, it can cause what's called hypoxia, basically oxygen starvation. So you get dizziness, headaches, shortness of breath, and some people even get that when they go to high altitudes. Even locally in the mountains, some people are really sensitive to that, and we call that just those dizziness, headache, shortness of breath. We call that altitude sickness. Okay, but if it gets really bad, you can become unconscious and even die. All right, so that's why we've got to be careful when climbing really tall mountains like Mount Everest. Now, on the other hand, in the other extreme, increasing the partial pressure of oxygen can also be dangerous to your body as well. So if you've scuba dived, or you plan on scuba diving, or know somebody who scuba dives, you know that as you go under the ocean, the pressure increases. In fact, you may even noticed it when you go to the bottom of a swimming pool. If you've ever, gone and touched the bottom, you feel that pressure in your ears. So the pressure increases when you go down into the depths. So at 30 meters, the air is at basically 4 atmospheres. So 30 meters down, the pressure increases to 4 times as much as we feel up here on the surface of the earth. So if we take, the partial pressure of that, that would be, 4 times 0.21, that's 0.84 atmospheres of partial pressure of oxygen. So that can also be damaging to our lungs. It can cause what's called oxygen toxicity. If there's too much oxygen, we get muscle twitching, tunnel vision, can get convulsions, and eventually death. So in scuba divers, their tanks have oxygen in them, okay, but they're not pure oxygen. It's actually what we call heliox. They have, sometimes they'll mix it with helium. Why not just more nitrogen? Well, an increase in nitrogen can cause nitrogen narcosis, which is like feeling tipsy or drunk. So too much nitrogen in the mixture is not good for our bodies as well. So heliox is pretty safe, and so we've got a mixture of helium and oxygen, and helium is not going to do, any damage to the lungs. It's a pretty light gas. All right, so there you go. It's some consequences of too low and too high pressure on our lungs. All right, so let's dig back into chemistry. All right, so sometimes when we have a chemical reaction, a gas will form. We've seen it before. We've mixed metals and acid, and we get gas bubbles that form. That's one that we've actually seen a couple of times in labs already. And there's others that could form as other reactions you could do that can form a gaseous product. So when the product of a chemical reaction is gas, it often is collected by displacement of water. We've actually never done this because unfortunately we don't have this apparatus. But what you could do is hook up a tube to your flask, and then the tube you invert a test tube or something in water. You fill it up and invert it, and then as the reaction goes, the gas, that bubbles out will go out and then displace the water. And so what we'll get is the gas being trapped there, right? So if we think about this, this reaction, let's just say it's the zinc with the hydrochloric acid. And so we're trapping, hydrogen gas, right? H2, hydrogen gas. So this hydrogen gas is being collected, but it's not actually pure hydrogen gas, because as it comes through, some of the water molecules are also becoming in gas form. So basically it's a mixture of hydrogen gas with a little bit of water vapor as well. So inside that little compartment right there, where that space is a gas, and it's putting pressure on the water, and that's how it's pushing the water out. So we call that, whenever a gas is putting pressure on a liquid, we call that vapor pressure. And so this is going to depend on temperature. So if you think about it, increasing temperature is going to increase the vapor pressure, because the molecules will be moving faster. They'll be taking up more space, which means that it has to put more pressure on the water to escape. So you'll probably hear vapor pressure, and that just means the pressure of the gas that is collected over a liquid. All right, so let's take a look at gases as they act in chemical reactions. So in reactions involving gas, reactants or products, the amount of gas is often specified in terms of its volume at a given temperature and pressure, meaning that a lot of times when you're working with problems and they're talking about gases, they're not going to say so many moles of gas. They're going to say this is the volume, the temperature, and the pressure, which means basically you have to use the Pivnert gas equation, right, that we talked about last time, PV equals nRT. So you'll have to put those numbers into this in order to solve for moles. So if you need to do any stoichiometry with this, you first would plug the numbers into Pivnert in order to figure out moles. And then for moles, you could go anywhere you need. So here, let's take a look at an example. So here we have a reaction, right? We've got hydrogen gas and nitrogen gas coming together to react to form ammonia gas. And it says how many moles of ammonia are formed by the complete reaction of 2.5 liters of hydrogen gas at 381 Kelvin and 1.32 atmospheres. All right, and we're going to assume that there's more than enough nitrogen to make this whole reaction go. All right, so what that means is that nitrogen is not our limiting reactant. So here, just like we were seeing before, we're given liters, Kelvin, and atmospheres. And so what we need to do then is plug it into our Pivnert ideal gas equation to solve for moles. And once we have moles, hey, we can plug it in using our stoichiometry to figure out how much ammonia is made. Okay, so when we plug in the numbers, okay, to our Pivnert, luckily for this example, we're working with the correct units, which is, remember, liters, Kelvin, and atmospheres. Have to have those. All right, and then we've also got the R, which is the constant here, 0.0821. So when we plug that all in, what we get is 0.11 moles of hydrogen. So in the reaction, if we have 0.11 moles of hydrogen, and we need to figure out how many moles of ammonia is made, right? Then we can just use the ratio 3 to 2. We'll set it up here. So we've got 2 moles of ammonia over 3 moles of hydrogen. The mole units are going to cancel when we do the math. We end up with 0.073 moles of ammonia. Okay, so we can do stoichiometry with gases and reactions. We just need to plug in the information given, the volume, the temperature, and the pressure into our ideal gas law to solve for moles. And then from moles, we can go anywhere it wants us to. All right, so here is one that you can try. Pause it for a few minutes after I'm done, explaining, and then try it, and then you can unpause it to see if you got it right. Okay, so in this example, it says how many liters of oxygen gas form when 294 grams of potassium chlorate completely reacts in this reaction. Okay, so here we've got the degradation of potassium chlorate, right, into potassium chloride and oxygen gas. And so this time we are given the reactants in terms of grams. And then we have to figure out the liters of oxygen. So we're going to use stoichiometry and we're going to use Pivnert, but we're going to use it in the opposite way that we just did in the previous example. So instead of plugging it into Pivnert first and then doing your stoichiometry, we're going to do stoichiometry first, right? And then we're going to plug the information into Pivnert in order to solve for volume, okay, or liters. Remember, liters is volume. So here it says, assume that the gas is collected at the pressure of 755 millimeters of mercury and 305 Kelvin. Now, before you pause and try this on your own, remember you have to be in atmospheres. So when it says millimeters of mercury, you need to convert that to atmospheres first. All right, so give it a pause for a few minutes and see if you can figure this out, and then we'll check ourselves. All right, so hopefully you did it correctly. Let's take a look. So the first step was to convert your 294 grams into moles. And so 2.4 moles is 294 grams of potassium chlorate is. All right, and then we plugged in those moles into the end spot in our PV equals nRT, making sure that we convert the 755 millimeters of mercury into atmospheres, which should have been 0.993. And when you solve for V, you should have gotten 60.5 liters. All right, let's take a look at another example. But before we do, you're going to run into problems where it talks about standard temperature and pressure. Okay, so here we've got, molar. Okay, so some gases that are at standard temperature and pressure are going to have the same volume, like a constant volume. So any gas that's at STP, which is standard temperature and pressure, any 1 mole of that gas is going to, at 1 atmosphere and 0 degrees Celsius, is going to contain or take up, I should say, 22.4 liters of volume. So STP is 1 atmosphere and 0 degrees Celsius, right? Or 273 Kelvin. So at that particular temperature and pressure, okay, any 1 mole of gas will always depend, doesn't matter what kind it is, any 1 mole of gas will take up 22.4 liters. Okay, so this is what we call the molar volume of gas at STP. So 1 mole of gas at STP equals 22.4 liters. So check it out. That's totally a conversion factor. So we can use this as a conversion factor in order to kind of solve some problems and take a little shortcut as long as we're working with the gas at STP. So here's an example. It says calculate the number of liters of carbon dioxide gas that forms at STP when 0.879 moles of calcium carbonate undergoes this reaction. So we have calcium carbonate degrading into calcium oxide and then carbon dioxide gas. So what we're given is the moles of calcium carbonate, so that's what we'll start with. We'll turn it into moles of calcium we're going to turn it into moles of carbon dioxide using our 1-to-1 ratio, right? And then because it says it's at STP, we can use the 1 mole, right? 1 mole of carbon dioxide equals 22.4 liters. And so if we do the math, we'll end up with the answer 19.7 liters. That's how much carbon dioxide gas will be formed during this reaction. All right, so this is our last slide and our last example problem. So this one says, how many grams of water form when 2.4 liters of hydrogen gas at STP completely react with oxygen? Okay, so here we've got water vapor being formed, and we need to figure out how many grams of that is going to form if we start out with 1.2 liters of hydrogen gas. So use what you know about STP and whatnot to convert this from liters of hydrogen to grams of water. So go ahead and pause it for a few minutes and then see if you're right. All right, so let's take a look and see if you did it correctly. So first off here, we're given liters instead of grams or moles, so we're going to kind of work backwards. We're going to turn liters into moles using our ratio of 1 mole equals 22.4 liters. And once we have the moles of hydrogen, then we can use the mole-to-mole ratio in our equation to turn it to moles of water. And then once we have moles of water, we can go to grams. So when we do all the math, what we're going to end up with is 0.998 grams of water. Okay, so hopefully that's what you got. All right, so that wraps up our lecture of gas mixtures and working with gases in chemical reactions, doing some stoichiometry with it. Hopefully it makes sense, and you guys can start working on the Chapter 11 homework questions for your exam, I think next week maybe. So just a heads up with that. All right, we'll see you next time.